Tonight's journey drifts to the quiet edge of the universe's biggest stars. Not the loud kind of biggest, but the careful kind, where a single number becomes a soft range, where distance, dust, and a fading limb decide what a radius really means. If calm science stories like this help you unwind, please tap like and subscribe. It tells the channel to keep making long, gentle, deep space documentaries. Now let the scale expand, let the definitions sharpen, and let the night grow still. A red hypergiant hangs in darkness like a low ember seen through thin fog. Biggest star sounds like a trophy, yet the word biggest changes with the method that tries to measure it. In that region, size depends on which edge is called an edge, and on how far the light is judged to travel. The first calm unlock is simple. A star can look enormous in one definition and ordinary in another. The scene begins as a broad reddish disk with a rim that thins into a dim skirt. The centre glows smooth and dense. The outer glow fades into darkness with no hard boundary. That fading rim is the first physical clue. It hints that a measured radius is partly a choice. The first core concept is angular size, meaning apparent width on the sky. Angular size is a tiny opening angle. It describes how large an object looks, not how large it is. A nearby pebble and a distant hill can cover the same patch of view. The same logic holds for stars. If the apparent disk spans a certain angle, the true radius depends on distance. The next unlock arrives without drama. Radius is angular size multiplied by distance. When distance shifts, the radius shifts with it. A signal would not announce the mistake. The result would simply look like a different star size. A slow visual anchor settles on the star's limb, the visible rim of the disk. The limb is not a wall, it is a slope in brightness. This leads to limb darkening, meaning the rim looks dimmer than the centre. Light behaves as a probe that samples different depths. Near the centre, the view reaches deeper layers that glow more strongly. Near the edge, the line of sight skims higher layers that are cooler and thinner. The unlock here is that the surface is a depth range, not a sheet. The measured outline can move depending on which depth is emphasized. A calm picture forms of layered glow. The brightness falls off like ink thinning in water. The boundary becomes a gradient with a soft edge. One safe scale anchor can be placed without claiming a final champion. Some of the most inflated stars reach about 1,000 times the Sun's radius. That corresponds to roughly 700 million kilometers. It is like a glowing sphere large enough to contain the orbit of a close inner planet inside its outer haze. The next unlock follows immediately. That vast figure can still change if the star's edge is defined differently. A different band of light can trace a different layer. A different fit to the limb can pick a different diameter. The same star can wear several plausible radii. The second core concept is distance error. Distance is an inferred quantity. It often comes from a subtle shift in position against distant background points. When that shift is tiny, uncertainty grows. A small relative error in distance produces the same relative error in radius. This is the quiet trap. Distance hides in the input. Radius appears in this headline. The limit of observation appears here in a soft way. The apparent disk can be close to the resolving power of the measurement method. The rim can blur into surrounding glow. Background light can leak into the edge. A fitted circle can still be drawn. Yet the circle may summarize a blur rather than a true boundary. The star's outer atmosphere adds another layer of uncertainty while remaining physically real. Gas can stream outward as a wind. The wind can form an extended, partially opaque envelope. In some wavelengths, the envelope acts like the visible surface. In others, it becomes nearly transparent. The visual returns to a candle behind frosted glass. The bright core is clear. The edge looks washed and soft, the unlock here is practical. A measured radius may describe the envelope more than the deeper photosphere. A record claim can be a claim about a layer. It can be true and still be incomplete. A gentle scale shift widens the view from the star's rim to the space between stars. Thin veils of dust and gas drift across long distances. Those veils dim and redden the light. If the dimming is misjudged, luminosity is misjudged. Then temperature estimates can drift. Then radius estimates drift through the link between temperature, luminosity, and area. The next unlock is that uncertainty often arrives as a chain. A small error in extinction can lead to a larger error in inferred radius. The chain is quiet and steady. It does not feel like a dramatic failure. It feels like a plausible answer that slides. Another visual anchor forms as mottled patterns on the disk. Vast convection cells rise and sink in the outer layers. Their brighter patches and darker lanes can shift the apparent limb by small amounts. Over days and weeks the pattern changes. Over longer spans the star itself can pulsate. A slow expansion and contraction can alter the outer layers. The unlock is that a single measurement can be a snapshot in motion. The largest value can coincide with an expanded phase. A later phase can be smaller without contradiction. The limit of intuition arrives gently at the end of this path. In everyday objects, edges are easy. A stone has a boundary, a cloud does not. These stars behave closer to clouds than stones. The rim is a gradient shaped by opacity's temperature and moving gas. A model can fit the gradient and yield a diameter, yet the fitted diameter depends on which brightness level is chosen as the boundary. It also depends on how distance is estimated. The mind prefers a single circle with a single number. The sky offers layered glow and gentle uncertainty instead. The section ends with a quiet forward step. The next stage focuses on the tiny angles themselves and on why they are so hard to measure at great distance. At this distance, a measured edge becomes a measured blur. The following section returns to angular size and the geometry that turns blur into radius. A distant stellar disk can be so small on the sky that its edge dissolves into pure suggestion. Biggest becomes uncertain when the apparent size is near the smallest angle that light can draw sharply. At this distance, angular size carries the entire story. The disk is not measured by walking around it. It is measured by how wide it looks in the dark. That width is an angle, not a length. Angular size means apparent width on the sky. It is a measure of spread, not of substance. The first quiet unlock follows at once. If the angle is uncertain, the radius is uncertain even before distance enters. The scene is a thin red coin of light held against a deep background of weaker glow. The rim is not crisp, the rim fades. The fade is a physical gradient. It is a slope from bright center to dim edge. That slope matters because any method that tries to mark an edge must pick a level on the slope. One choice finds a larger disk. Another choice finds a smaller disk. The second calm unlock appears within the same image. A changing edge threshold can change size without changing the star. The next core concept is the wave blur that follows light itself. Light behaves as waves that spread and overlap. When waves from a tiny disk are gathered into a single image, the waves do not settle into a perfect circle. They form a small blur pattern. The pattern has a bright tone. It has faint rings around it. The rings are a physical structure in the light. The rings soften the boundary of any tiny object. The primary visual anchor becomes those rings. In that region, a small disk does not end at a hard line. It ends inside a halo made of concentric ripples. The primary analogy fits the shape. It resembles ripples from a raindrop on still water. The center is strongest. The rings weaken outward. The first payoff inside this concept is simple. Even a perfect disk in space becomes a softened spot in light. The edge is not lost through carelessness. The edge is limited by wave behavior. The scale shifts gently from the star's vast radius to the tiny angle it subtends. A giant star can span a huge physical width, yet the sky can compress it into an angle that is almost nothing. A useful number can sit here without strain. The apparent width can be about 1/1,000,000th of a circle, like a fine pencil dot seen from far across a wide plane. That number is not a claim about one star alone. It is a safe way to feel the smallness. The payoff arrives immediately. When the angle is that small, a tiny change in the blur pattern can change the inferred diameter. The next slow visual anchor rests on two faint disks near each other. Their halos overlap, their rings mix. The combined spot looks broader than either disk. The overlap can make two objects appear as one larger object. It can also make one disk's rim seem to extend farther. The unlock here is careful and calm. Crowding can imitate size. Even when the star is alone, background glow can play a similar role. A diffuse haze can raise the faint outer light. The rim can be pushed outward in the fit. The disk can appear inflated. The third core concept is how uncertainty propagates through distance. A radius is not read directly. It is computed from angle and distance. If both have uncertainty, the product has compounded uncertainty. The logic is plain. A small fractional error in distance creates the same fractional error in radius. A small fractional error in angular size does the same. The same star can land in a wide band of plausible radii. The result can still be consistent with physics. It can still be consistent with the same light. The payoff is that largest often means largest within uncertainty. It is a range claim, not a single sharp verdict. A slow scene returns to the limb again. The centre is bright and steady. The edges are low slope. The halo rings sit on top of that slope. The edge is now a blend of two softening effects. One comes from the star's own atmosphere. One comes from wave blur. In that blend, a clean boundary does not exist. The limit of observation becomes clear in a gentle way. When the blur pattern is broader than the true disk is not resolved. The measurement then relies on modelling. The model assumes a brightness profile. It assumes how the limb fades. It assumes how the halo rings distribute light. If those assumptions are slightly wrong, the inferred diameter slides. This is not a failure of effort. It is a limit of resolution and of indirect inference. The mind prefers edges that can be traced. Here the edge is a probability curve drawn from light. Another visual anchor settles on a thin annulus, a faint ring of light around the disk. The ring is not a physical ring around the star. It is the wave pattern in the gathered light. Its presence can be helpful. The spacing of rings relates to how sharply the system can define detail. Yet it also reveals the constraint. The rings show that the image is not a direct imprint of the star. It is a transformed pattern. The payoff arrives again. The same transformation can be stable and still limit certainty. A star can be the same every night. The measurement can still carry a flaw of ambiguity. A quiet scale shift widens from moments to long spans. The star evolves over hundreds of thousands of years. Its radius can change over those spans, yet the measurement uncertainty can be large enough to hide small changes. Even short-term pulsations can blur into the error bars if sampling is sparse. The result is a calm paradox. A star can breathe in radius. The reported radius can stay the same, or a star can stay steady. The reported radius can drift as methods change. This is the human free way the data behave. A signal would not say which part is physical and which part is method. It would only arrive as light with structure. The section ends with a gentle forward motion. The next stage places distance at the centre of the uncertainty. It returns to the quiet shift of position that sets the scale of space. From that point, angular size becomes a length. The following section moves into distance errors and why they dominate many biggest claims. A star's place among faint background points can drift by a hair's breadth without the star moving at all. Distance becomes the main uncertainty because the same tiny shift must be turned into a vast scale. In that region, parallax is the key idea. Parallax means apparent position change from a shifted viewpoint. The first unlock is quiet and immediate. A small apparent shift implies a far distance. A large shift implies a nearer distance. The sky offers a slow visual anchor. A bright point sits near a thin triangle of dim specks. Over a full cycle of motion, the triangle seems to flex. The bright point slides slightly within it. The motion is not a streak. It is a gentle repositioning. The background specks remain almost fixed. The bright point does not. Light behaves as geometry here. Two lines of sight are separated by a baseline. The baseline is the distance between the two viewpoints. A larger baseline makes the shift easier to see, a smaller baseline makes it harder. A single safe number gives the scale of the baseline in a calm way. The widest baseline in a full orbit corresponds to the distance light travels in about 17 minutes. It is like a long pause stretched into space. With that baseline, even a tiny shift can be meaningful. The second unlock follows at once. When the shift is extremely small, any uncertainty in the shift becomes a large uncertainty in distance. The radius then inherits that uncertainty. The scene returns to the bright point and its faint neighbours. The bright point does not change brightness much. Its position changes relative to the background. The change can be drawn as a small ellipse on the sky. The ellipse is a trace of viewpoint motion. The physical detail is subtle but real. The star's apparent position has a seasonal wobble. The wobble is a shadow of distance. The analogy stays ordinary and unique. It resembles judging depth in a clear pond by shifting viewpoint. A nearby pebble seems to move against deeper sand. The sand appears almost still. The pebble shifts more. The unlock is that the background provides a reference plane. Without a stable reference, the shift has no meaning. In the sky, the reference is made of many faint points. Yet those points are not perfectly fixed. Some have their own slow drift across time. Some are close enough to share the wobble. This introduces the limit of observation. The inference relies on relative positions that are smaller than many blurring effects. When light spreads into a soft spot, the center of that spot must be located. When background points crowd together, the center can be pulled. When the star's own light has a halo, the halo can bias the centroid. The shift becomes a statistical estimate. It is not a simple mark on a crisp map. The third unlock arrives with this limit. Even perfect geometry cannot rescue a shift that is below the available angular detail. The distance then becomes a broad range. The radius becomes a broad range as well. A slow visual anchor changes to a quiet ladder of distances. Nearby stars show clear shifts. Farther stars show smaller shifts. At the far end, the shift becomes almost invisible. The scale shifts from local neighborhoods to distant regions where the background thickens. The star field becomes denser. The faint points blend into a grainy fog. In that fog, the bright star's small wobble is harder to isolate. The calculation can still proceed. It proceeds by combining many measurements across time. It uses repeated snapshots of relative position. The payoff is gentle. Time itself becomes part of the ruler. A longer time span can improve distance. Yet time also introduces new complications. Background points drift. The target star can drift too. That drift is called proper motion. Proper motion is true motion across the sky. Parallax is apparent motion from viewpoint shift. The two motions can overlap. So they can pull in different directions. Separating them requires modelling. This modelling is another limit of inference. If the time coverage is uneven, the model can trade one effect for another. A small parallax can be mistaken for part of a straight drift. A straight drift can be mistaken for part of a parallax ellipse. The unlock is that distance is not read directly. It is extracted from a mixture of motions. The physical picture becomes clearer with another slow image. The star's path on the sky is a thin curve. The curve is made of a steady slide plus a small loop. The loop is the parallax. The slide is the proper motion. The loop can be tiny. The slide can be larger. The loop can be lost if the curve is noisy. At this distance, a signal would not declare which part is loop. The separation must be inferred. This is where distance errors grow. A small error in distance becomes a proportional error in radius. The star's apparent angular size from earlier sections then turns into a physical size with a wide uncertainty. The next unlock connects back to the largest stars. A red hypergiant can appear enormous in angle if it is near. The same apparent angle can imply a far star with a much larger radius. Distance decides which interpretation is allowed. The trophy word biggest then rests on a fragile foundation. It rests on a tiny loop measured against faint points. It rests on a baseline that is vast yet still finite. It rests on the ability to locate the center of a blurred spot. Another scale shift eases outward. Over thousands of years, a star's true motion changes its sky position noticeably. Over a single year, parallax adds a small seasonal loop. Over a single night, flickering conditions can shift apparent centers. These timescales overlap. The result remains calm. Distance is achievable but never absolute. It arrives as an estimate with a margin. That margin is the hidden part of any radius claim. The section closes with a soft transition toward light itself. Distance is only one half of the puzzle. The other half is how bright the star seems after light crosses space. In the next section, dimming and reddening by drifting dust begin to shape radius uncertainty. A bright star can arrive looking gently muted, as if its light has passed through a quiet veil. Radius uncertainty grows when dimming and reddening are mistaken for the star's own nature. In that region, extinction becomes the first core concept. Extinction means light loss as it crosses drifting dust and gas. The first small unlock is immediate. If arriving light is dimmer than assumed, the star is judged less luminous. If luminosity is judged lower, the inferred radius can shrink. The visual anchor settles on a broad dust lane that cuts across a dense star field. The lane is not a line, it is a gradient from faint haze to near black velvet. Along its edge, pinpoints of light fade unevenly. Some points remain sharp, others look softened and weakened. The physical detail is the lane's soft boundary and layered thickness. In that layered boundary, extinction is not uniform. The next unlock follows calmly. Patchy dimming creates a false precision. A single average correction can miss local pockets of deeper shadow. The second core concept is reddening. Reddening means shorter wavelengths are removed more strongly. It shifts the balance of colours in the arriving light. The dust grains act like tiny scatterers. They redirect and absorb more blue than red. Light behave as a stream that loses its cooler tones first. The sky then carries a warmer cast. The star can seem cooler than it is. That matters because temperature helps set radius when luminosity is also inferred. A gentle analogy holds this without strain. It resembles a stack of pale tea-stained papers placed over a white page. Each sheet dims the page. Each sheet also warms its appearance. The first payoff here is clear. Dimming and warming can imitate a larger, cooler star or a smaller, hotter one. The same arriving light can support more than one physical story. A quiet scale shift widens the scene from a single line of sight to a whole region. Dust does not sit as a smooth fog, it forms filaments, clumps, and layered sheets. Over a small patch of sky, extinction can vary. Over larger spans, the variation becomes a map of shadows. The star's radius estimate then depends on where the line of sight threads those shadows. A single path can pass through a denser knot. Another path can pass through clearer space. The next unlock is gentle and practical. Two stars with similar true sizes can look very different if dust differs. The method that ranks biggest can then rank the cleanest sightline. The visual returns to the dust lane edge. The lane has a scalloped boundary. Its darkness thickens inward. At the boundary, faint halos appear around some points. The halos are not a physical shell around the stars. They are scattered light in the surrounding haze. The physical detail is this soft aureole that merges with the background glow. That glow can be mistaken as part of a stellar disk in some conditions. It can push an inferred edge outward. It can also make the background brighter. A brighter background can hide the faint outer limb of a real disk. Another payoff appears here. Dust can both inflate and deflate a radius estimate depending on how the edge is separated from its surroundings. A single correction is rarely neutral. The section leans into one simple number for scale. A dimming by a factor of 2 is like turning a lantern down to half brightness. Inverse judgment then follows. If half the light is lost and not recognized, luminosity is cut in half. If temperature is held fixed, inferred radius drops by about the square root of 2. The number stays soft in the ear. The comparison stays ordinary and calm. The unlock is that modest dimming can create a noticeable radius change. The same effect becomes larger when dimming is stronger. The limit of observation arrives quietly. Dust properties are not fully known along each line of sight, grain sizes vary, composition varies. Clumps vary. The exact reddening curve can shift with environment. When the curve is uncertain, separating intrinsic colour from dust colour becomes ambiguous. A star can appear red because it is cool. A star can appear red because dust removed the bluer light. When only the arriving spectrum is available, the two causes can trade places in a model. That is the limit of indirect inference. The radius then inherits a systematic uncertainty. It is not just random scatter, it is a bias that can push the answer in one direction. The visual anchor shifts to a quiet pocket inside the lane. The pocket is darker but not empty. A few points shine through with a subdued glow. Their light looks softened like paint seen through waxed paper. The physical detail is the layered translucence. Within that pocket light that survives is weighted toward longer wavelengths. The next payoff is small and steady. A radius estimate built on brightness and temperature can drift when the spectral balance is altered. The drift can be mistaken for a real change in the star. A calm scale shift extends from moments to long spans. Dust structures can drift and evolve over thousands of years. Yet even without motion, different sightlines sample different layers. Over a single season of measurement, the dust is essentially fixed. The uncertainty remains. Over many years, improved mapping of dust can reduce it. Still, local knots can remain unresolved. The edge of certainty remains soft like the lane's own boundary. A signal would not label which photons were lost. It would only arrive diminished. Another slow scene forms at the lane's fringe. The darkness thins into a translucent mist. The background points brighten. The mist shows faint striations like layered smoke frozen in place. Those striations reveal that extinction is structured. They also suggest why a single average correction fails. The unlock is a return to the theme of biggest. A star can be ranked largest because its line of sight is clearer. Another star can be demoted because dust made it seem smaller or cooler. The ranking can change as dust models improve. This change does not mean the star changed. It means the path of light was understood better. The section closes with a gentle turn toward the star itself. Even with dust accounted for some stars wear extended outer layers that blur what surface means. The next section moves from the space between stars to the star's own wind and envelope, where the edge can expand into a luminous haze. A giant star can look larger than it is because its own atmosphere becomes part of what light reveals. Biggest can shift when an extended wind creates a new visible boundary beyond the deeper surface. In that region, the first core concept is optical depth. Optical depth means how opaque a layer is to light. The early unlock is calm and direct. The visible surface sits where opacity becomes about 1. That surface can move outward if the wind thickens. The visual anchor begins as a red globe with a soft aureole. The core is bright and steady. Around it lies a faint shell that glows unevenly. The shell is not a hard ring. It is a layered haze. Its brightness falls off with a smooth gradient. The physical detail is that gradient and the way it thickens in some directions. The star's edge becomes a zone, not a line. The second core concept is mass loss. Mass loss is outflow of gas from the star. The outflow can carry dust and molecules. It can also carry ionized gas that scatters light. The flow is not static, it moves outward and it can form arcs and partial shells. The quiet payoff arrives here. An outflow can create a larger apparent radius without changing the deeper layers. A star can keep its core size while wearing a larger coat. Light behaves as a probe that stops where it is absorbed or scattered. In a thin atmosphere, light escapes from deeper layers. In a thicker wind, light escapes from higher layers. The apparent disk then grows. The analogy stays ordinary and unique. It resembles a street lamp inside a thick winter fog. The lamp's bulb is fixed. The glowing sphere around it expands as fog thickens. The boundary of that glow is not sharp. It is a smooth fade. The unlock is immediate. Measuring the glow's diameter does not equal measuring the bulb. In that same way, measuring a wind-shaped photosphere does not equal measuring the deeper star. The visual returns to the halo. Its outer rim is faint. It is still present. A ring-like transition appears where the glow drops faster. That transition can be mistaken for a surface, yet it is only a change in opacity with radius. The physical detail is a shell boundary where density falls. Density is not constant in a wind. It often declines outward. When the decline is slow, the photosphere is pushed outward. When the decline is steep, the photosphere sits closer in. The next payoff arrives. Two similar stars can show different apparent radii if their winds differ. The third core concept is wavelength dependence. The wind is not equally opaque at all wavelengths. Some wavelengths are absorbed by molecules, some are scattered by electrons, some pass through more easily. The visible radius can therefore depend on which observed light is used to trace it. A disk measured in one band can be larger than in another band. This is not contradiction. It is layered structure. The visual anchor shifts to a quiet onion of translucent shells. Each shell has a different transparency. One shell is thin and clear, another is thicker and milky. The glow's edge is placed on these different shells depending on the wavelength. The payoff is simple. One star can have multiple radii, each linked to a different layer. A single number then becomes a chosen convention. A calm number can illustrate scale without overreaching. The wind can extend the apparent radius by a factor of 2. That is like a coat that doubles a silhouette in thick snow. The deeper body does not double. The outline does. The unlock follows right away. A factor of 2 is large enough to reorder a ranking of biggest stars. A star can climb the list because its wind is dense. It can fall when the wind thins. The limit of observation enters softly. The outer halo is faint. It can sit near background levels. Separating halo light from surrounding glow becomes difficult. The inference then relies on fitting a brightness profile. The fit assumes a form for how density drops with radius. It assumes how scattering behaves. It assumes the halo is symmetric or at least smooth. Yet winds can be clumpy. They can have arcs. They can have preferred directions. When asymmetry is present, a simple radius is an average. The measured radius then hides structure. This is a limit of modelling and of resolution. The halo can be detected. Its shape can still be uncertain. The next visual anchor slows on a partial shell a curved arc in the outer glow. The arc is brighter than the surrounding haze. It suggests a denser layer of outflow material. The arc is not a closed ring. It is incomplete. It fades into darkness. The physical detail is the arc's curvature and its sharp inner edge. The payoff is quiet. A single diameter cannot capture a star wrapped in arcs. Choosing a radius becomes choosing how to compress complexity into one number. The scale shift widens from the star's edge to the timescale of outflow. Gas leaving the star drifts outward over years and decades. Layers can pile up into shells. Over longer spans, mass loss can reshape the star's future. Yet the apparent radius can change on shorter spans as the wind density changes. The ranking of biggest can then be time-dependent. The star can appear to swell when outflow is thick. It can appear to contract when the outflow thins. The deeper star may change more slowly. The halo can change faster. The unlock is that the apparent edge is not a permanent feature. It is a moving boundary set by opacity. Light behaves as a moving frontier. Where light escapes marks the surface. Where light is trapped lies beneath. The frontier shifts with density. It shifts with the wavelength. It shifts with structure. The section ends with a gentle bridge toward variability. Winds often accompany pulsation and convection that can modulate density and temperature. The next section follows that breathing rhythm and shows how a changing radius can be real and how a changing radius can be apparent within the same calm light. A star can seem to breathe in and out even when its distant light stays calm to the eye. Radius changes can be real through pulsation and can also be apparent through shifting layers. In that region, pulsation is the first core concept. Pulsation is a rhythmic expansion and contraction. The early unlock is quiet. A measured radius is a phase, not a permanent identity. The visual anchor settles on a red disk with a faint limb that slowly thickens and thins. The The center remains bright. The rim's gradient steepens, then relaxes. A slight bulge forms in the outer glow, then recedes. The physical detail is that changing gradient at the limb and the way the edge slides across it. The cycle is not abrupt. It is slow. It resembles a gentle tide in a dark ocean. The first payoff arrives quickly. When the limb moves, the radius definition moves with it. A star can appear larger because the same brightness level sits farther out. The second core concept is phase. Phase is the position within a cycle. It is the difference between early expansion and late contraction. This matters because measurements taken at different times can disagree without conflict. A single claim of biggest can pick a moment near maximum extension. A later measurement can find a smaller radius and still describe the same star. A calm analogy holds this in a single image. It resembles a slowly inflating and deflating bellows covered by cloth. The cloth marks the outline. The frame beneath changes. The outline changes too. The unlock is simple. A radius can be a moving target even before any distance uncertainty enters. The visual anchor deepens. The disk's edge is a slope of light. A thin layer above the deeper surface becomes more opaque during expansion. During contraction, density rises closer in. Light behaves as a boundary seeker. It escapes where opacity becomes low enough. If opacity changes with phase, the visible surface shifts. This yields a quiet payoff. Yet, the visible radius can change more than the deeper radius because the escape layer moves. That is an apparent change added to a real change. A gentle scale shift widens from the limb to the star's interior. The outer atmosphere is thin compared to the whole star, yet it controls the visible outline. A small adjustment in density or temperature can move the escape layer outward by a large fraction of the atmosphere's thickness. That small shift can look like a large radius change. The core remains hidden. The outline carries the news. The next payoff follows. Measurement methods that track the outline can overstate structural change if the escape layer shifts strongly. A single safe number can place the cycle in time. Some large pulsating giants vary over about 1 year like a slow seasonal rhythm. That span is like waiting through 4 quiet seasons. The radius can be near maximum for part of the cycle and smaller for the rest. The unlock is immediate. A radius reported without phase is like a tide height reported without the moon's position. The sky then becomes a series of snapshots with no shared timestamp. The third core concept is convection, though kept in a gentle form. Convection is heat moved by rising and sinking gas. It creates mottled regions on the surface. Those regions can change the apparent limb. Bright patches near the edge can make the disk appear broader in a fit. Dark patches can do the opposite. The visual anchor shifts to slow drifting islands of brightness. The islands are broad. They have soft borders. They slide across the disk over time. The physical detail is the patch edge, and its contrast with the surrounding glow. Another payoff appears. The measured radius can change when surface patterns change, even if the average structure stays similar. The limit of observation enters softly. The disk is tiny. The limb is a gradient. The measurement often relies on fitting a model brightness profile. If the star's brightness is asymmetric, the fit may force symmetry anyway. The model then invents a best radius that averages over true structure. This is a limit of resolution and of modelling. The difference between a real radial change and a shifting brightness pattern can be hard to separate. A signal would not label the cause. It would only arrive as a changing profile. Another visual anchor settles on a faint shell beyond the disk. The shell brightens slightly during expansion. It fades during contraction. The shell is the wind region from the prior section. Its opacity can be modulated by phase. This yields a calm payoff. The coat can swell and shrink as density waves pass outward. The deeper star can be steadier. The visible boundary can still move. The analogy remains unique and quiet. It resembles a lantern wrapped in a thin, breathing fabric sleeve. The lantern remains the source. The sleeve expands and contracts. The sleeve defines the outer glow. The unlock is clear. One star can present multiple radii across time and across layers. A ranking of biggest becomes a ranking of moments and definitions. A gentle scale shift widens toward long evolution. Over thousands of years, the star's average radius changes as it moves through late stages. Over months and years, pulsation adds a wave on top of that trend. Over nights, convection patterns rearrange the limb's fine shape. These timescales layer together like slow music. Measurement uncertainty can hide some of them. Improved monitoring can reveal them. Yet the boundary remains soft because the star remains layered. The limit of intuition appears gently here. Everyday objects do not change size by shifting an invisible surface outward. Yet stars have no solid wall. The visible surface is a condition, not a boundary. Treating the outline as a rigid skin can mislead. The section closes with a soft transition toward rotation and shape. A star that spins quickly can flatten. A flattened star has more than one radius. The next section follows this quiet distortion and shows how angle and orientation can change into what biggest seems to mean. A star can be wide in one direction and narrow in another, while still appearing calm and round at first glance. Biggest can become an orientation question when rotation reshapes the body and its light. In that region, oblateness is the first core concept. Oblateness means flattened shape from rotation. The early unlock is plain. A single radius is not enough for a flattened star. The visual anchor settles on a luminous oval with a gentle bulge at its middle. The poles look slightly tucked in. The equator looks slightly pushed out. The rim is still a gradient, yet the gradient is not identical everywhere. Along the equator, the fade stretches farther. Near the poles, the fade tightens. The physical detail is the changing curvature and the different limb gradients around the disk. The second core concept is gravity darkening. Gravity darkening is cooler equator and hotter poles. It arises because surface gravity differs with latitude in a rotating star. Light behaves as a map of temperature and brightness. Where gravity is stronger, layers compress. Heat escapes differently. Where gravity is weaker, the outer layers puff. This yields a calm payoff. The brightest parts of the disk may not mark the widest parts. A radius inferred from brightness can drift toward a preferred latitude. The star can be widest at the equator. The star can look brightest near the poles. The disk can then appear smaller or larger depending on how the brightness profile is interpreted. A unique analogy holds this without strain. It resembles a spinning mound of soft dough. The dough flattens at the top. It spreads around the middle. The surface is not equally smooth everywhere. The center can look raised while the rim spreads. The unlock is immediate. Shape and brightness can separate. The visual anchor deepens with a slow change in orientation. At one orientation, the oval looks obvious. At another, it looks nearly circular. The same star presents different apparent geometry. When the spin axis points toward the line of sight, the equatorial bulge is hidden in projection. When the axis lies sideways, the bulge becomes visible. The next payoff arrives. A star can seem to change size across measurements if orientation is unknown. Different methods can weight different parts of the disk. Some methods emphasize the brightest regions, some emphasize the faint outer limb. A model that assumes symmetry can average these differences into a single radius. That single radius may not match any real latitude. A gentle scale shift widens from surface shape to global consequences. Rotation alters the star's effective temperature pattern. That pattern alters the inferred luminosity. Luminosity then feeds the inferred radius in energy balance relations. A small geometric flattening can produce a wider systematic effect. The disk's brightest zone can bias temperature upward. The outer faint limb can bias radius upward. These biases can pull in opposite directions. The unlock is calm and useful. Disagreements between radius estimates can trace back to which latitude is being sampled. A single safe number can illustrate magnitude without overclaim. A fast rotator can have an equatorial radius about 1.5 times the polar radius. That is like an orange squashed into a gentle loaf. It is still roundish, yet the difference is real. The payoff follows at once. A ranking of biggest based on one radius can miss the other radius. If the equator sets the largest extent, that becomes one definition of biggest. If a mean radius is used, the star may drop in rank. If the polar radius is used, it drops further. The limit of observation enters softly. The disk is small, the limb is faint. The difference between oval and circle can sit near the measurement floor. The inference then relies on fitting an ellipse to a blurred brightness field. If the blur pattern is stronger than the flattening can be washed out. If surface brightness is uneven, the fitted ellipse can tilt or shrink. This is a limit of resolution and of modelling assumptions. A signal would not announce the axis direction. It would only arrive as a slightly asymmetric distribution of light. Another slow visual anchor appears as a faint band across the disk. The band is not a physical ring around the star. It is the equatorial zone where brightness is lower. The band is broad, it has soft edges, it makes the disk look as if a dim belt lies across it. The physical detail is that belt-like gradient and how it merges into the limb. The payoff is quiet. A dim equator can make the widest region harder to detect. The measured edge may be pulled inward along the equator. The star can then look less wide than it truly is. In contrast, a fit that follows the faint belt's outermost trace can push the radius outward. The answer depends on method choices. The scale shift widens towards time. Rotation is stable over many cycles, yet surface patterns can drift over days and months. Pulsation from the previous section can modulate the flattening slightly. A wind can add a halo that hides asymmetry. The combined picture is layered. Shape affects brightness. Brightness affects inferred temperature. Temperature affects inferred radius. Another payoff arrives. A star's record size can change when improved models include rotation. The star itself may not change. The interpretation changes. The limit of intuition appears gently. Everyday objects have a clear edge and a fixed shape. A spinning star has no rigid boundary. It has a moving layered surface shaped by gravity and heat flow. A single radius is an approximation. The approximation can be adequate for many uses. It can be misleading when searching for the biggest. The section ends with a soft transition towards systems with two stars. In pairs, overlapping light and mutual motion provide another way to infer size. The next section follows eclipses and orbital geometry where shadows and timing reveal radii without relying only on a blurred limb. Two distant lights can circle in darkness and reveal size by the way one glow slides across the other. Radius can be constrained by timing when an eclipse sketches an edge. In that region, the first core concept is an eclipsing binary. An eclipsing binary is a pair that blocks each other in line. The early unlock is calm. The duration of dimming encodes the chord length across a disk. The visual anchor begins as two soft disks. One disk is slightly larger and redder. The other is smaller and paler. They drift across each other with steady motion. As overlap begins, the combined light fades. The fade is not a step. It is a smooth ramp shaped by limb gradients. The physical detail is the curved shadow boundary, a moving arc that sweeps across the brighter disk. The arc is a clean geometry even when edges are soft. The next payoff arrives. A curved shadow boundary can reveal size even if the disk is not fully resolved. The second core concept is the light curve. A light curve is brightness change over time. It is a quiet record of overlap. It rises and falls like a gentle valley. The bottom can be flat if one disk fully covers the other. The bottom can be rounded if coverage is partial. The slopes can be steep or shallow depending on limb darkening and relative sizes. This yields a calm unlock. Shape of the valley reveals more than its depth. The timing of the ingress and egress gives relative radii in units of orbital separation. The analogy stays ordinary and unique. It resembles two translucent coins sliding over a lamp. As the overlap grows, the room light dims. The dimming rate depends on how fast the coins move and how large they are. The first payoff is immediate. Timing gives size ratios without needing a sharp image of the disks. The visual anchor deepens as the overlap reaches the midpoint. The shadow arc crosses the center. The brightest core is covered. The combined glow shifts to the uncovered limb where brightness is lower. The physical detail is the brightness gradient across the covered disk. The limb darkening makes the eclipse asymmetric in feel. Covering the center removes more light than covering the rim. The light curve records this. The next payoff follows. Limb darkening can be used as a tool rather than a nuisance. If the limb darkening profile is modeled, the radius constraint tightens. Yet modeling introduces limits. The third core concept is orbital geometry. Orbital geometry is the shape and tilt of the path. The path may not pass through the center. It may skim near the edge. This sets the impact parameter, the offset of the crossing chord. A chord near the center is long. A chord near the limb is shorter. The same pair can produce different eclipse durations at different tilts. This yields a calm unlock. Duration alone does not give absolute radius unless geometry is known. Geometry can be inferred from the pair of eclipses and the depth pattern. Still, degeneracies can remain. A gentle number can place the scale of the timing. An eclipse can last about 1 day. That is like watching a slow dimming through a full night and day. In that span, the shadow arc moves across a disk that is immense in physical size. Yet the timing is measured in ordinary time. The payoff is quiet. Huge radii can be mapped into hours and days. This mapping makes eclipses feel like clocks. The scale shift widens from the disk edge to the orbit. The orbit can be far larger than either star. Yet the eclipse depends on the exact line of sight. A small tilt change can remove eclipses entirely. In that region, a signal would vanish if alignment changes. This shows a limit of intuition. The sky's full of pairs. Only a few align to eclipse. The presence of eclipses selects special geometry. The inference rests on that selection. The limit of observation enters softly. Light curves are integrated signals. They do not show a picture of the disks. They show only total brightness. When two disks overlap, multiple combinations of radius limb darkening and impact parameter can produce similar curves. Noise can blur small features. Variability from pulsation can add gentle waves on top of the eclipse valley. This is a limit of modeling and of separation of effects. The method can still constrain radii well. It can still leave uncertainties that matter for biggest claims. Another slow visual anchor appears at secondary eclipse. The smaller disk is hidden behind the larger. The total light drops by a smaller amount. This depth difference reveals the relative surface brightness. The physical detail is the slight change in the valley depth and the smoother shoulders. The payoff follows. Two eclipses together can break some degeneracies. The ratio of radii becomes clearer. The ratio of brightness becomes clearer. Yet absolute scale still needs orbital separation in physical units. That separation depends on distance or on dynamical constraints derived from motion. Without direct velocity, information separation can remain in relative terms. The biggest claim then remains conditional. A pair can show one star much larger than the other. It may still not yield an absolute radius without additional anchors. The visual anchor returns to the moving arc. The arc is a clean curve in darkness. It glides across the limb gradient. It defines a boundary even when the limb is soft. The payoff is calm. Eclipses draw edges with shadow, not with brightness thresholds. This can be more stable than direct imaging in some cases, yet even shadow depends on atmospheric extension. A wind halo can cause a gradual onset. The eclipse then starts early in faint layers. The modelled radius can reflect the halo rather than the deeper photosphere. This returns to layered radii. The scale shift widens again toward long time. Over years, repeated eclipses refine period and timing. Small timing changes can indicate orbital evolution. Yet for radius measurement, stability helps. When the period is steady, the radius constraint from timing becomes steady. When pulsation shifts the photosphere, the eclipse contact times can shift slightly. That shift can mimic a radius change. The limit of observation then returns. Separating true orbital timing from changing stellar layers requires long coverage and careful models. A signal would not separate them by itself. It only supplies the valley of light. The section ends with a gentle bridge toward the next mechanism. When eclipses are not available, size can still be inferred from brightness, temperature, and distance. That path returns to energy balance. The next section moves into the link between luminosity, temperature, and radius. where small uncertainties become large inferences. A star's size can be inferred from how much energy escapes even when the disk itself remains too small to picture. Radius becomes a derived quantity when luminosity and temperature are combined into area. In that region, luminosity is the first core concept. Luminosity is total light power emitted. The early unlock is calm. If luminosity is overestimated, radius is overestimated. If luminosity is underestimated, radius shrinks. The visual anchor begins as a glowing sphere floating in blackness. Its light falls away with distance in a smooth gradient. The nearby space is bright. Farther out, the glow thins into darkness. The physical detail is the spherical fall-off of brightness and the soft halo that fades into the void. A simple idea hides in the fading. The same star looks dimmer when farther away. Distance must be known to turn apparent brightness into luminosity. That link returns to earlier sections. Distance errors become luminosity errors. Luminosity errors become radius errors. The first payoff appears here. The chain does not need complicated physics. It needs only one missing step. The second core concept is effective temperature. Effective temperature is the temperature of a blackbody with same color. It is a simplified temperature tied to spectrum shape. It is not a thermometer at a point. It is an overall descriptor. Light behaves as a mix of wavelengths. When the spectrum is shifted toward red, the temperature inference can drop. When shifted toward blue, it can rise. Dust reddening from earlier sections can mimic cooler temperature. Gravity darkening from rotation can bias temperature. The payoff is quiet and immediate. Temperature errors do not stay small. They enter radius through a strong dependence. A modest temperature shift can move radius significantly when luminosity is held. The unique analogy holds this relationship gently. It resembles judging the size of a heated stone by its glow and color. A smaller stone can glow brightly if very hot. A larger stone can glow the same if cooler. The unlock is plain. Brightness alone does not set size. Color sets temperature. Temperature and brightness together set area. The visual anchor deepens into a slow change in color gradient across the disk. The center looks warmer. The limb looks cooler due to limb darkening. If the disk is unresolved, that gradient is not seen. Yet it still shapes the integrated light. The physical detail is the hidden temperature gradient that affects the spectrum. The next payoff follows. An integrated spectrum can conceal spatial structure. The derived temperature is an average. The derived radius then becomes an average radius tied to an average temperature. The scale shift widens from a single star to a region of space. In a crowded field background, light can add a faint pedestal under the star's brightness. That pedestal can make the star appear brighter than it is. It can raise inferred luminosity. It can inflate inferred radius. In a dark field, the opposite occurs. The measurement depends on how the star is separated from its surroundings. The next payoff is calm. Even when the physics is correct, the inputs can be biased. The radius inherits the bias without warning. A safe number can anchor the sensitivity without strain. If luminosity is off by a factor of 2, inferred radius shifts by about the square root of 2 when temperature is fixed. This is like drawing a circle whose area doubles. The radius grows, but not by double. The payoff is immediate. Moderate luminosity errors create noticeable radius changes. The same sensitivity becomes sharper when temperature is uncertain. The limit of observation arrives softly. Luminosity requires a bolometric correction, a conversion from measured band to total output. Bolometric correction is the adjustment from partial light to full light. It depends on spectrum shape. If the spectrum is distorted by dust or by winds, the correction becomes uncertain. The derived luminosity can drift. This is a limit of modelling. It is not a limit of arithmetic. The star's real emission may include infrared from dust, ultraviolet from hot regions, and scattered light from an envelope. Capturing all of it is difficult. When only part is seen, the correction can become a guess guided by templates. A signal would not announce what is missing. It would only deliver what passes through. Another visual anchor forms as a thin, cool envelope around the star. The envelope absorbs short wavelengths and re-emits at longer wavelengths. The halo is faint, it is extended. Its brightness is low but spread over a large area. The physical detail is the broad, low-surface brightness glow that can be missed. The payoff is quiet. Missing the halo underestimates luminosity. Underestimated luminosity shrinks radius. Including the halo without separating it from the star inflates radius. The definition of what belongs to the star becomes part of the measurement. The scale shift widens again towards time. Over months and years, pulsation changes temperature and brightness. A single epoch luminosity and temperature can reflect a phase. The derived radius then reflects that phase. Over long spans, stellar evolution shifts average temperature and luminosity. The derived radius follows. Yet uncertainties in extinction and bolometric correction can be comparable to these changes over shorter spans. The limit of intuition appears gently. In everyday life, a brighter object often seems larger. In stellar physics, a brighter object can be smaller if hotter. The mind can misread brightness as size. The derived radius corrects that misreading. It does so only if temperature is correct and luminosity is complete. When those inputs are uncertain, the correction can overshoot. The section ends with a soft bridge toward definitions of radius itself. Even if luminosity and temperature are known, a star's surface is layered. Different layers emit different light. The next section moves into radius definitions and the idea that several shells can each be a legitimate boundary for the same star. A star can have several honest edges, each one revealed by a different way light escapes. Biggest depends on which layer is chosen as the boundary and which wavelength traces that layer. In that region, the first core concept is the photosphere. The photosphere is the layer where most light escapes. The early unlock is quiet. The photosphere is not a solid surface. It is a depth range where opacity drops enough for light to leave. The visual anchor begins as a glowing sphere wrapped in translucent shells. Each shell is faint. Each shell has a slightly different brightness. The inner shell looks smooth and steady. The outer shell looks mottled and thin. The physical detail is the layered gradient like a stack of vels where no single veil is the edge. Light behaves as a traveller that stops at different depths depending on wavelength. In one band, light escapes deeper. In another band, light escapes higher. That means each band draws a slightly different disk. The first payoff appears here. A star can have multiple radii that are all correct within their definitions. The second core concept is opacity. Opacity is how strongly material blocks light. It depends on temperature density and composition. It also depends on wavelength. In cooler outer layers, molecules can form. Those molecules absorb specific bands. In hotter regions, ionized gas can scatter. Scattering can create a broad halo. The boundary then becomes a wavelength-dependent gradient. A unique analogy holds this gently. It resembles looking into a lake that contains layers of foggy water. A blue-lighted beam stops in the upper murk. A red beam reaches deeper. The lake has one water level, yet the visible depth changes with colour. The unlock is simple. Seeing does not always equal reaching. The visual anchor deepens to the limb darkens. The limb also thickens into a softer skirt at certain wavelengths. The physical detail is the limb's changing slope, sometimes steep and sometimes extended. In an extended atmosphere, the limb can gain an extra shoulder. That shoulder can look like a second edge. A measurement method that picks a brightness threshold can lock onto that shoulder. Another method can lock onto the deeper limb. The payoff follows. A reported radius can quietly encode a method choice. It can also encode a wavelength choice. The third core concept is radius definition. A definition is a rule for where the edge lies. One definition might use where intensity drops to half the center. Another might use an optical depth condition. Another might use where a fitted model reaches a certain level. Each definition yields a different number. Each can be useful. The biggest claim then depends on which definition is used. A gentle scale shift widens from a single ray of light to the full atmosphere. Near the deeper photosphere, density is higher. Above it, density falls by many orders of magnitude. The fall is smooth. There is no wall. A small change in the chosen optical depth can move the defined radius outward through a large physical distance in a supergiant. The next payoff arrives. A tiny change in a definition can become a large change in kilometers. The star has not changed. The map line has moved. A single safe number can anchor the sense of layering. The photosphere thickness can be about 1% of the radius in a large star. That is like the skin of a peach compared to the whole fruit. Yet in absolute distance it can still be enormous. The payoff is calm. A thin fractional layer can be a vast space. That space can hold molecule formation zones and scattering layers. Each zone can become a different edge in different light. The visual anchor shifts to a broad band around the star where faint absorption appears. The band is not a physical belt. It is a region where opacity rises. It can make the apparent disk larger in that band. It can also make the disk's limb look softer. The physical detail is the band's diffuse boundary and the way it blends into the halo. The limit of observation enters softly. When the disk is not resolved, radius definitions must be inferred from integrated spectra and models. Models assume temperature gradients and density profiles. They assume how molecules form. They assume how winds carry material outward. If these assumptions are wrong, the inferred optical depth surface can be misplaced. This is a limit of modeling and of indirect inference. A signal would not announce which layer produced which photons. It would only deliver a blended spectrum. Even with resolved data, the faint outer limb can sit near background glow. Separating limb from background can be ambiguous. This creates a flaw of uncertainty in any edge definition. Another payoff appears. The faintest layers can dominate uncertainty while contributing little to total light, yet those layers can add a large radius offset. They can also vary with time. A wind density change can thicken an outer shell. The shell then shifts the optical depth surface outward. A pulsation can modulate temperature and molecule formation. The defined radius in a molecular band can grow and shrink. The deeper continuum radius can remain steadier. The scale shift widens to timescales again. Over nights, the edge can wobble through changing opacity. Over years, mass loss can reshape the envelope. Over thousands of years, evolution shifts the whole structure. The layered radius definitions respond differently to each timescale. The limit of intuition appears gently. In solid objects, there is one boundary. In a star, the boundary depends on the question asked. Is the boundary where most light leaves? Is it where a chosen wavelength becomes opaque? Is it where a model sets optical depth? Each answer is a boundary with its own meaning. The biggest label then becomes conditional. It can still be useful. It must be paired with the definition used. The section ends with a quiet transition toward how improvements accumulate. Better distance mapping, better extinction mapping, and better modeling can narrow these definition gaps. The next section moves into long-term refinement, where repeated measurements and improved sky catalogues steadily reduce uncertainty in the largest star claims. A measurement can sharpen over time even when the star remains far beyond any clear picture. Biggest becomes less fragile when many small uncertainties are reduced together. In that region, cross-calibration is the first core concept. Cross-calibration is combining multiple methods to constrain one quantity. The early unlock is calm. Different errors point in different directions. When methods agree, confidence rises. When they disagree, the disagreement maps the uncertainty. The visual anchor begins as a quiet web of faint points and gentle arcs. Each arc is a possible distance. Each point is a possible radius. Where arcs overlap, a small bright cluster appears. The physical detail is the convergence region where separate constraints intersect. Light behaves as a messenger that can be interpreted in several independent ways. Parallax provides distance. Eclipses provide size ratios. Spectra provide temperature. Extinction maps provide corrections. Each provides a partial angle on the same star. The first payoff appears. A single method can mislead. A combined set can reveal which part is unstable. The second core concept is systematics. Systematics are biases that push measurements in one direction. They are not random noise. They can persist across datasets. Dust reddening can bias temperature low. Crowding can bias brightness high. Wind halos can bias disk size high. Rotation can bias temperature high in bright poles. The payoff is gentle. Systematics can cancel or compound depending on which methods are used. Cross-calibration can expose them by forcing consistency across physical relations. A unique analogy holds this quietly. It resembles measuring the width of a river with several ropes. One rope stretches, another sags. A third is stiff. Only where their limits meet does the true width appear. The unlock is immediate. Agreement is not a vote. It is a geometry of constraints. The visual anchor deepens to a set of layered shadows and glows. A faint dust lane cuts across the field. Nearby, a pair of disks overlaps in a slow eclipse. Farther out, a single disk shows a soft halo. Each scene contributes a different kind of uncertainty. The physical detail is that each uncertainty leaves a different signature. Dust leaves a color tilt. Crowding leaves a raised background. Halos leave extended wings in brightness profiles. Eclipses leave smooth ramps in time. Parallax leaves small loops in position. The next payoff follows. Each signature can be tracked across repeated observations. Repetition is quiet power. The third core concept is time baseline. A time baseline is the span over which data are collected. A longer baseline improves separation of effects. Parallax loops are annual. Proper motion is linear over years. Pulsation cycles can be months to years. When the baseline is long, these patterns can be separated. When the baseline is short, they can blend. A gentle number can anchor the baseline without strain. 10 years is like a long shelf of seasons. Over 10 years, parallax cycles repeat 10 times. This repetition stabilizes an average. The payoff is calm. Repetition turns a faint loop into a reliable signal. It also allows identification of outliers and phases. The scale shift widens from nightly data to decade-long catalogues. A single night yields a snapshot. A decade yields a map of trends. The radius of a variable star can be folded over its cycle. The mean radius can be compared to model expectations. The wind halo can be monitored for changes. Dust maps can be refined as more stars are sampled along the same sightlines. The next payoff arrives. Many small improvements can reduce the tail of extreme radius claims. The largest stars often sit in that tail. As the tail tightens, some record holders move. The limit of observation enters softly. Even with long baselines, some uncertainties remain stubborn. Very bright stars can saturate in some data. Very dusty regions can hide blue light. Very extended halos can blend into background. Very crowded fields can confuse centroids. These are limits of dynamic range and of resolution. They are not easily solved by more time alone. Modelling remains necessary. Modelling can improve, yet it carries assumptions. A signal would not reveal the true halo boundary if it falls below background glow. It would only provide an upper limit. Another slow visual anchor appears as a faint annulus around the star barely above darkness. The annulus is the outermost detectable halo layer. It is smoother in some directions and ragged in others. The physical detail is the raggedness implying clumps in the outflow. The payoff is quiet. Clumpiness can be mistaken for a larger radius if averaged. It can also be mistaken for background if missed. Combining wavelengths can help. If a halo is stronger in one band, it may be weaker in another. This difference can separate halo light from background. Yet wavelength differences also introduce definition differences from earlier sections. The combined approach must be careful. The scale shift widens again toward physical models. Stellar evolution models provide expected luminosity and temperature for given stages. Atmosphere models provide limb darkening and opacity profiles. Wind models provide expected halo extents. When observational results disagree with models, the disagreement can indicate real physics or model weakness. This introduces a limit of interpretation. A correction can be applied in the wrong direction if the model is wrong. Cross-calibration can reduce this risk by comparing multiple independent models and datasets. Still, deep uncertainties can remain for the most extreme stars. The payoff is gentle and honest. The biggest stars are often the hardest to measure because they are rare, distant, and complex. The section closes with a soft transition toward consequences. As uncertainty shrinks, the meaning of biggest becomes more precise. The next section follows how revised radii reshape estimates of mass loss, lifetime, and eventual fate without relying on any single record holder. A star's radius is not only a size, it is a lever that changes how easily matter can drift away. When radius estimates shift predictions for mass loss and remaining lifetime shift with them. In that region, surface gravity is the first core concept. Surface gravity is the pull felt at the visible surface. The early unlock is calm. A larger radius usually means weaker surface gravity at the same mass. Weaker gravity makes the outer layers easier to lift into an outflow. The visual anchor begins as a luminous globe with a soft extended skirt. The skirt is not uniform. It shows faint bands and scalloped edges. A slow stream of gas drifts outward. The stream is thin near the surface. It becomes broader and more diffuse farther out. The physical detail is the smooth density gradient in that skirt and the way it breaks into wisps. Light behaves as a tracer of where gas becomes thin enough to glow. The first payoff appears. If the visible surface is defined farther out, the pull at that surface is smaller. Models then predict a higher outflow for the same star. A star can seem more fragile simply because the chosen radius is larger. The second core concept is mass loss rate. Mass loss rate is how much matter leaves per time. It is not measured by touch. It is inferred from how gas absorbs and emits light. A larger radius can raise the inferred mass loss rate in two ways. It weakens surface gravity. It also changes the density needed for the same optical depth. The next payoff follows. A small change in radius can change how thick the wind must be to create the observed halo. The halo then becomes a sliding ruler. The visual anchor deepens to the outer skirt. A faint arc appears where density drops faster. Beyond the arc, the glow becomes grainy. The graininess is clumping. Clumping means gas gathers into dense knots. The physical detail is the knotty texture and the dark gaps between knots. Clumping matters because light interacts more strongly with dense gas than with thin gas. If gas is clumped, a line can look strong even if total mass is lower. The payoff is calm and direct. Ignoring clumping can inflate a mass loss estimate. Treating the wind as smooth can overstate how much matter is leaving. A unique analogy holds this gently. It resembles estimating how much mist fills a valley by watching how a distant light beam fades. If the mist is smooth, fading maps total mist. If the mist sits in patches, fading can be dominated by the patches. The valley can look thicker than it is. The scale shift widens from a thin shell to a vast envelope. The wind occupies an enormous volume compared with the photosphere thickness. Yet the wind can still contain only a small fraction of the star's mass at any moment. This contrast is a quiet lesson. A huge halo does not automatically mean huge mass. The next payoff arrives. The largest apparent stars can be those with the most extended optically active outer layers. Those layers can be light in mass but large in radius. A single safe number anchors the uncertainty without strain. Clumping can change inferred mass loss by about a factor of 3. That is like estimating snowfall from a landscape with drifts. The drifts look deep. The average depth is smaller. The payoff is immediate. An uncertainty of 3-fold can alter predicted lifetime and final core mass. The limit of observation enters softly. Mass loss is inferred from line profiles, continuum excess, and halo brightness. Each inference depends on geometry and on opacity. If the wind is asymmetric, an average model can mislead. If dust forms in some regions, light can be absorbed and re-emitted elsewhere. If the halo fades into the background, the outer boundary becomes uncertain. This is a limit of resolution and of indirect inference. A signal would not label whether absorption comes from a smooth sheet or from knots. It would only deliver a blended imprint. The visual anchor shifts to a slow spiral-like pattern in the outer glow. The pattern is faint and incomplete. It is a density wave in the outflow. The physical detail is the gentle curvature and the way brightness peaks along the curve. Such structure can arise from pulsation and rotation interacting with the wind. The payoff is quiet. Structure means that the wind cannot be treated as a single number at all radii. A mass loss rate measured close in may not match the rate farther out. Time variability can be written into the halo as layered arcs. The scale shift widens again towards time. A wind layer near the star reflects the last months or years. A far layer can reflect earlier decades. The halo becomes a slow archive of outflow episodes. Yet the archive is incomplete. Faint layers can be missed. Bright knots can dominate. This produces another payoff. The most dramatic halo features may not represent the average outflow. They can represent rare episodes. Radius estimates that include those episodes can overstate the typical radius. That can feed back into model predictions of mass loss. The third core concept is remaining lifetime. Remaining lifetime is the time left before core conditions change decisively. For very massive stars, remaining lifetime can be about 10 million years. That span is like a brief spark on the scale of planetary history. The payoff is calm. Even large uncertainties in late-stage mass loss occur within a short cosmic interval. A revised radius can change the estimated mass loss rate. A revised mass loss rate can change how quickly the star sheds its outer layers. Shedding outer layers can change surface temperature and spectrum. That then feeds back into the radius definition through opacity and colour. The chain is circular and gentle. It is also sensitive. The limit of intuition appears softly. In everyday objects, losing material means shrinking. In a star, losing mass can coincide with an expanded cool envelope for a time. The visible radius can stay large even as mass is reduced. The star can look enormous while becoming lighter in its outermost layers. The section closes with a soft transition toward the long view. Revised radii and revised mass loss reshape predictions for the star's final structure. The next section widens to how these revisions change expectations for end states and for the surrounding medium while keeping the tone steady and unhurried. A giant star does not only occupy space, it also reshapes the space around it long before any final change. Radius revisions change the volume of the surrounding envelope and the strength of its influence. In that region, the first core concept is the circumstellar medium. The circumstellar medium is gas and dust surrounding a star. The early unlock is calm. A larger inferred radius often implies a larger and denser nearby environment in models. The visual anchor begins as a warm sphere floating in darkness. Around it, a faint cocoon spreads outward in layers. The inner layer looks smooth and bright, the outer layer looks thinner and grainier. The physical detail is a set of nested gradients that fade like soft shells with no hard edge. Light behaves as a traveller that scatters and reddens when it passes through grains. The cocoon, therefore, changes what distant light looks like. That change feeds back into the inferred temperature and luminosity. The first payoff arrives. A star can look larger because its cocoon alters the light that defines size. The cocoon can also be larger because the star is larger and cooler. Cause and effect can loop gently. The second core concept is optical depth. Optical depth is how opaque a layer is to light. When optical depth is high, light emerges from higher layers. When optical depth is low, light escapes from deeper layers. In a wind cocoon, optical depth can vary with direction. It can vary with wavelength. It can vary with time. The next payoff follows. A radius defined by optical depth can shift outward without any change in the deeper layers. The cocoon becomes the apparent surface in certain bands. This does not require a thick wall. It requires only enough material along a long path. The visual anchor slows toward the limb. The limb is not a clean rim. It is a soft skirt that merges into the cocoon. The skirt shows faint filaments. The filaments curve and dissolve. The physical detail is the filamentary edge and the way brightness falls in a long tail rather than a sharp drop. The unique analogy holds the feeling without strain. It resembles a cloud bank at dawn seen from a distance. The cloud bank has a bright core. Its edges are frayed. The edge depends on the threshold used to define it. The unlock is immediate. The star's edge can be an adopted contour on a gradual fade. The scale shift widens from the photosphere to the surrounding parsec scale. The cocoon can extend far beyond the visible disk. It can carry memory of earlier outflow episodes. A dense inner layer can reflect recent years. A diffuse outer layer can reflect earlier centuries. The next payoff arrives. Measurements taken in different wavelengths may sample different epochs of the outflow. A band that traces warm dust may emphasize older layers. A band that traces hot gas may emphasize newer layers. The apparent radius can then shift with the chosen tracer. A single safe number anchors the surrounding scale. The cocoon can reach about 1 light year. That is like spreading the star's influence across a region as wide as a slow year of light. The payoff is calm. Even a thin cocoon can fill a huge volume. A huge volume can still contain little mass if density is low, yet its effect on light can be strong because the path is long. The third core concept is ionization. Ionization is atoms losing electrons due to energetic radiation. In the inner cocoon, ionization changes how gas absorbs and emits. Ionized gas scatters light differently than neutral gas. It can also glow in specific lines. Those lines can be used to infer density and outflow structure. The next payoff follows. Radius revisions can change predicted ionization balance near the star. A larger radius at similar luminosity implies a cooler effective temperature. Cooler conditions can reduce ionizing output. The inner cocoon then stays more neutral in models. A more neutral cocoon absorbs and reddens differently. The measurement loop tightens again. The visual anchor shifts to a boundary in the cocoon. The boundary is not a wall. It is a transition zone where the glow changes character. Inside the gas is smoother and brighter. Outside the glow becomes faint and mottled. The physical detail is that transition zone, a broad front that curves around the star like a dim arc. The payoff is quiet. A front like this can be mistaken for a larger photosphere if spatial resolution is limited. It can also be missed if background brightness is high. The limit of observation enters softly. The cocoon is low in surface brightness. Its outer parts can blend into the field. Separating cocoon light from unrelated background is difficult. This is a limit of contrast and of resolution. Even when the cocoon is detected, converting brightness into mass requires dust properties. Grain sizes and compositions vary. Assumptions about grains can shift inferred optical depth. They can shift inferred cocoon extent. A signal would not label which grains are present. It would only deliver a reddened spectrum and a faint halo. Another limit appears in time. The full evolution of a massive star is far longer than a single observing campaign. The envelope seen today is one frame in a long sequence. Models must connect frames into a story. This is a limit of inference from snapshots. The next payoff arrives. When radius uncertainties shrink, envelope uncertainties often shrink as well, because the same inputs control both. Better distances improve luminosity. Better extinction improves temperature. Better temperature improves radius. Better radius improves surface gravity estimates. Those improvements refine predicted outflow density near the star. The cocoon becomes less ambiguous as a physical structure rather than a vague halo. The scale shift widens again toward the star's eventual fate. If a star ends in a rapid core transition, an outward-moving disturbance meets the cocoon first. The cocoon then shapes how that disturbance radiates. A denser cocoon can turn energy into light earlier and longer. A thinner cocoon can let energy escape more quickly. The payoff is gentle. Uncertainty in radius can become uncertainty in how bright and how extended the surrounding emission becomes during the final phase. Yet even here definitions matter. A radius tied to deep optical depth may not represent the cocoon. A radius tied to a molecular band may sit within the cocoon. Two studies can therefore predict different surroundings from different radius choices. The visual anchor returns to the nested shells. The inner shell is bright and smooth, the outer shell is faint and wide. The shells drift outward at different epochs. The physical detail is the layering itself like rings in a quiet fog that records past changes. The section ends with a soft transition toward perspective and ranking. Once cocoon and radius definitions are laid side by side, biggest becomes a family of answers rather than a single trophy. The next section widens to how uncertainty bands and definitions reshape the sense of records across the sky, and how a gentle precision replaces a simple label. A record list can feel simple, yet every entry hides a quiet band of uncertainty around it. Biggest becomes clearer when the band is shown as part of the answer. In that region, uncertainty interval is the first core concept. An uncertainty interval is a range that could contain the true value. The early unlock is calm. Two stars can overlap in interval even if one has a larger central estimate. Then the ranking is not a clean line. It is a soft braid of possibilities. The visual anchor begins as a dark sky scattered with faint points. Around a few points, translucent rings appear. Each ring is a radius interval turned into a halo on a chartless canvas. Some rings overlap, some are separate. The physical detail is the overlap itself, like pale circles crossing and creating a darker shared region. Light behaves as a messenger with a margin of error. The margin grows when distance is uncertain. The margin grows when extinction is uncertain. The margin grows when the edge definition is uncertain. The first payoff arrives. A record claim is often a statement about the lower limit of one star exceeding the upper limit of another. If that condition is not met, the record is provisional. The second core concept is propagation of error. Propagation of error is how uncertainties combine through calculations. Radius depends on distance and angular size. If distance is slightly wrong, radius shifts in direct proportion. If angular size is slightly wrong, radius shifts too. When both have uncertainty, the range widens. The payoff is immediate. A modest uncertainty in two inputs can create a large uncertainty in the final radius. The visual anchor deepens to a slow, quiet comparison. One star shows a clean limb in one band. Another shows a softer limb with a halo. The physical detail is the limb's slope difference and the faint outer glow. A measurement that fits the clean limb yields a tighter interval. A measurement that includes the halo yields a wider interval. The ranking can invert depending on definition. This does not mean one study is careless. It means the object is complex. The unique analogy holds this gently. It resembles comparing the height of two trees in fog. One tree has a sharp silhouette, the other fades into mist near the top. Any measured height depends on where the fading is called the top. The unlock is calm. The softest edge produces the widest uncertainty band. The scale shift widens from a single measurement to a population. In a large survey, many stars are measured with similar methods. Systematic biases can then be mapped. If many stars in a region share a distance bias, their radii share a bias. If many stars share a dust model error, their temperatures share a bias. The ranking can then shift as a group when the bias is corrected. The next payoff arrives. A revised catalogue can move several candidates up or down together, not one at a time. This changes how records should be read. A list is not a ladder. It is a snapshot of a moving calibration. A single safe number can anchor a sense of overlap without strain. If uncertainty is about 20%, it is like measuring a room length by pacing with uneven steps. The reported number is useful, it is not exact, the payoff is immediate. A 20% band on a very large radius can span an enormous physical distance. That span can cover the difference between a record and a runner-up. It can also cover different radius definitions. The limit of observation enters softly. For the largest and most distant stars, angular size can be below the resolving power in many bands. Then angular size is inferred. Inference relies on models of brightness distribution and limb darkening. If limb darkening is wrong, angular size shifts. This is a limit of resolution and of model dependence. A signal would not announce whether the assumed brightness profile matches the real one. It would only provide a pattern that several profiles can fit nearly equally well. Another limit appears in the sky itself. Crowding blend sources. Background nebulosity adds uneven glow. Both can inflate brightness and alter inferred luminosity. Both can shift the radius through temperature fitting. This is a limit of contrast and of source separation. The visual anchor shifts to a crowded field where faint points sit inside a milky haze. The haze is not uniform. It has gradients and knots. The physical detail is the uneven background that makes a star's edge harder to define. The payoff follows. When background is structured, the faint halo around a star can be either real envelope or background glow. This ambiguity widens uncertainty. It also encourages conservative reporting. Conservative reporting often means larger intervals. Larger intervals reduce the chance of a false record, yet they also make rankings less crisp. The third core concept is definition tag. A definition tag is a short label for which radius is meant. A radius can be continuum-based. A radius can be molecular band-based. A radius can be halo-traced. Each tag changes comparability. The payoff is gentle. Two stars can be compared only when their tags match or can be converted reliably. Without tags, a record list mixes quantities. Mixing quantities inflates apparent drama. It creates artificial record breaking. With tags, the story becomes steadier. The scale shift widens toward the meaning of biggest. Biggest can mean largest photosphere. Biggest can mean largest effective emitting surface in a chosen band. Biggest can mean largest envelope extent at a given optical depth. Each meaning has its own purpose. A record list can then become a set of lists. Each list has clearer rules. Each list has clearer uncertainties. The limit of intuition appears softly. In everyday ranking, the top item is definitive. In cosmic measurement, the top item can be a region. It can be a set of candidates whose intervals overlap. That overlap is not failure. It is an honest map of knowledge. The payoff arrives. The most stable outcome is not a single champion. It is a narrowed band for several contenders with well-stated definitions. The visual anchor returns to the translucent rings. Over time, the rings become thinner. Some rings drift as calibrations improve, some separate, some merge. The physical detail is the changing thickness of the rings like tightening circles on a dark surface. The section ends with a soft transition into closure. Once definitions, intervals, and limits are held together, biggest becomes a calmer statement. The next section resolves the arc by returning to what radius means physically and by settling into a gentle, precise understanding without suspense. The largest stars remain largest in a quiet way, even when the exact edge refuses to be pinned down. The calm answer is simple. Biggest is a definition plus an uncertainty band, not a single perfect circle. At this distance, the first core concept is the photosphere. A photosphere is the layer where light last scatters before escaping. The early unlock settles gently. A star's radius is the location of a chosen photosphere in a chosen band. The visual anchor opens on a red supergiant suspended in darkness. Its light is not sharp. Its limb fades through a long gradient. The center glows like a steady ember. The edge looks like a soft breath dissolving into space. The physical detail is that gradient. It has no hard boundary. It has a slow fall in brightness that changes with wavelength. Light behaves as a traveler that changes its last scattering depth with color. A redder band emerges from higher layers. A bluer band can emerge from deeper layers. The first payoff arrives. Two radii can both be correct when they describe two different last scattering layers. The second core concept is optical depth. Optical depth is how much a layer blocks light. When optical depth is about one, light escapes from that height. When optical depth is higher, light escapes from above it. When it is lower, light escapes from below it. This builds a calm checkpoint. The apparent surface shifts outward when opacity rises. It shifts inward when opacity falls. The star does not need to expand for the apparent radius to move. The visual anchor drifts closer to the limb. The limb looks like stacked haze. Fine ripples cross it. The ripples are slow brightness bands. They hint at convection cells beneath. They also hint at a turbulent atmosphere above. The physical detail is the mottled limb. It is not uniform. It carries a faint patchwork that blurs at the edge. The next payoff follows. When the edge is patchy, a single angular size can depend on how the patchwork is averaged. Different methods can weight the bright patches, different methods can weight the darker lanes. A small change in weighting can shift a radius estimate. A gentle scale shift arrives. The scale moves from a single patch on the limb to the full envelope. A patch can span a distance larger than many planetary orbits. The full star can be about 1,000 solar radii, like a sphere that reaches beyond the orbit of Jupiter. The number stays simple. The comparison stays familiar. The payoff is calm. A record size can be true in order of magnitude while the exact boundary remains uncertain. The third core concept is the uncertainty interval. An uncertainty interval is a range that could contain the true value. In that region, the record is not a spike. It is a band. Two candidates can overlap in band. One can lead in central value, another can lead in lower bound. Both statements can coexist. The visual anchor widens to a quiet set of stars. Each star is a dim point with a faint halo. Each halo has a thickness that represents the interval. Some halos touch, some halos separate. The physical detail is the overlap region where halos layer into a darker shade. The next payoff arrives. When intervals overlap, the most honest ranking is a group of contenders with shared space. This reduces drama. It increases clarity. It also explains why the record seems to change when a catalogue updates. The update often shrinks or shifts the intervals. Another checkpoint appears. Distance uncertainty often sets the width of the interval. If distance shifts, radius shifts with it. Extinction uncertainty also matters. Dust changes the spectrum. Spectrum changes temperature. Temperature changes how radius is inferred from luminosity. The payoff is immediate. A distance correction can revise a record without any change in the star itself. It is a calibration change. The limit of observation enters softly and clearly. Many of the largest stars are too small in angular size to be resolved cleanly at their true distance. The edge must then be inferred from how light is distributed. This is a limit of resolution and of model dependence. A signal would not reveal whether the assumed limb profile is unique. It would allow several profiles that fit nearly the same. Another limit joins it. The surrounding field can be bright and structured. Nebulosity can add gradients. Crowding can blend faint sources. This is a limit of contrast and of separation. The visual anchor shifts to a faint star embedded in a milky veil. The veil has knots and wisps. Some wisps arc across the star's halo. The physical detail is that uneven veil. It makes the halo's edge harder to isolate. The payoff arrives. When the background is structured, the safest radius interval becomes wider. Wider intervals resist false certainty. They also make record claims more cautious. The calm arc turns toward meaning. Biggest can mean the largest photosphere in a continuum band. Biggest can mean the largest molecular layer where opacity rises. Biggest can mean the largest dust-influenced surface in the infrared. Each meaning answers a different physical question. The unique analogy holds this gently. It resembles drawing a shoreline on a quiet beach after a long swell. The water does not have a single edge. The wet sand fades into dry sand through a broad zone. A line can be drawn at one chosen dampness level. Another line can be drawn at a different level. Both lines describe the same beach. They describe different definitions of the edge. The payoff is immediate. A star's edge can be a chosen contour on a smooth fade, not a physical wall. The scale shift widens towards time. The outer atmosphere responds in hours and days. The interior evolves over millions of years. Both timescales share one consequence. A measured radius is a momentary surface in a long story. The calm story does not need a single champion to feel complete. It needs a clean definition, a clear interval, and a stable order of the magnitude. The visual anchor returns to the red supergiant. Its limb fades again into darkness. The mottled patches drift in slow motion. The halo remains faint and wide. The physical detail is the final gradient and the quiet disappearance of the edge. The last payoff settles like a soft landing. Measuring the largest stars becomes less about declaring a winner. It becomes about learning how light chooses its last surface in a layered atmosphere. It becomes about learning how distance and dust shape what is called size. It becomes about accepting that biggest is a careful phrase that carries its own margin. The closing transition stays gentle and complete. In that region, the sky holds many large stars without rivalry. The measurements refine slowly. The definitions remain clear. The calm understanding remains steady.